We can perform operations on rational expressions in much the same way we do with rational numbers. We'll start with multiplication, then do division. Look at the product 2/7 times 3/5. Recall that when multiplying rational numbers, you simply multiply the numerators and denominators together. So a rational number becomes 2 times 3 divided by 7 times 5, which equals 6 divided by 35. To recall the definition of multiplication of rational numbers, we have P divided by Q times R divided by S equals P times R divided by Q times S, where P, Q, R, and S are real numbers. We'll use the same method when multiplying rational expressions. Let's look at a simple rational product. X plus 1 divided by x minus 1 times x plus 1 divided by x plus 2. Instead of having a single integer, we now have polynomials in the fractions. But we know how to multiply polynomials. This rational product can be rewritten as x plus 1 times x plus 1 divided by x minus 1 times x plus 2. If we use FOIL here to multiply the binomials, we get x² plus 2x plus 1 divided by x² plus x minus 2. If you wanted to, you could have left the denominator factored and just squared one of the binomials in the numerator. X plus 1 squared divided by x minus 1 times x plus 2. This form will be considered simplified by most. What about dividing? Now I won't get too advanced yet because very soon we will cover something known as complex fractions, which by definition is division of fractions. But for now, we're going to look at division of rational numbers through the method of multiplying by the inverse. This is the same method we used when dividing rational numbers. Take a look at 3/4 divided by 4/5. To divide these two rational numbers, we take the inverse of one and multiply it to the other. So let's take the inverse of the second rational number and multiply it to the first. 3/4 times 5/4, which equals 15/16. Once again, we can recall our definition for the division of two rational numbers. P over Q divided by R over S equals P over Q times S over R, which equals P times S divided by Q times R, where P, Q, R, and S are real numbers. Let's try using a rational expression now. 2x minus 3 divided by x plus 1 divided by x minus 1 divided by x plus 1. We'll start by inversing the second expression. 2x minus 3 divided by x plus 1 times x plus 1 divided by x minus 1. Note that it usually doesn't matter which expression you choose to inverse. Multiplying across gives us 2x minus 3 times x plus 1 divided by x plus 1 times x minus 1, which simplifies to 2x minus 3 divided by x minus 1. These types of expressions can become quite diverse in how they are applied and approached. Working through a few basic examples may help us to understand how to multiply, divide, and simplify them. Number 1. 2x plus 3 over 4x to the fourth plus 16x squared plus 16 times 2x squared plus 4 over 2x plus 3. We're asked to multiply two rational expressions. Let's rewrite the two expressions as a single expression, making sure to keep the two original expressions separated with parentheses. 2x plus 3 times 2x squared plus 4 divided by 4x to the fourth power plus 16x squared plus 16 times 2x plus 3. We should now recognize that 2x plus 3 will divide out to 1, leaving us with 2x squared plus 4 divided by 4x to the fourth power plus 16x squared plus 16. Using the factorization theorem, you would see that we can factor the denominator, which will look like this: 2x squared plus 4 divided by 4x to the fourth power plus 8x squared plus 8x squared plus 16. Note that even though the factorization theorem gave us the square root of 0, it still works because the square root of 0 equals 0. Let's finish this with grouping and simplify. 2x squared plus 4 divided by 2x squared times 2x squared plus 4 plus 4 times 2x squared plus 4. This equals 2x squared plus 4 divided by 2x squared plus 4 squared, which equals 1 divided by 2x squared plus 4. Number 2, 90x squared plus 60xy divided by 6x plus 9 times 1 divided by 6x plus 4y. There are some large numbers here, and even two variables this time around. However, that doesn't always mean it's going to be a hard problem. First, combine the expressions together. 90x squared plus 60xy divided by 6x plus 9 times 6x plus 4y. Let's go ahead and factor out the numerator. 30x times 3x plus 2y divided by 6x plus 9 times 6x plus 4y. I think I see a pattern. Let's factor out the GCF from each of the terms in the denominator. We can factor out a 3 from this term and a 2 from this term. 30x times 3x plus 2y divided by 6 times 2x plus 3 times 3x plus 2y. We can now simplify by dividing out some terms, which will lead us to 5x divided by 2x plus 3. Notice that all those large numbers and even the y variable completely disappeared from our expression, making it much more simpler. Number 3, x cubed divided by x minus 4 divided by x cubed divided by 5x squared minus 20x. Now we're asked to divide two rational expressions. We see some large degree variables in this expression, but remember, we're learning to simplify these so that we don't need to work with the large variables. First, we'll inverse one of the fractions so we can get rid of the division symbol. X cubed over x minus 4 times 5x squared minus 20x over x cubed. Now we'll combine our two expressions. X cubed times 5x squared minus 20x divided by x minus 4 times x cubed. The x cubed will divide out, and then we can factor the numerator. 5x times x minus 4 divided by x minus 4. The factored binomial will divide out with the denominator, leaving us with 5x. I cannot stress enough how important it will be to master simplifying these expressions. As I've showcased, we often have difficult expressions that can be made much easier to work with. There will be many times in algebra and calculus where if you don't have a grasp of simplifying these, your work will suffer. It's not often that you have to divide rational expressions the way we were shown here today. As a matter of fact, I can't think of a single instance. That's not to say we won't be dividing rational expressions. They just don't appear like we saw today. There's a lesson coming up soon about that. My main reason for showing this kind of division was to introduce you to the technique of multiplying rational expressions by the inverses. In the next lesson, we'll focus on the addition and subtraction of rational expressions.